Hello, students. I'm going to try to get you these answers back to you before the weekend so you can enjoy your long weekend without thinking about how you did on your test. All right, I'm going to do the open-ended problems first. Empirical formula means the lowest whole number ratio, and the way we do that is um, we're going to rewrite these percentages into grams. So for phosphorus, um, and this is under the assumption we have 100 grams of this compound. And so if you have 100 grams of this compound, 56.38 grams of it would be phosphorus, because percent means per 100. Okay, and so the reason we're doing this is because we need to find the moles. All right, so oxygen is 43.62%, and if we had 100 grams of the compound, we would have 43.62 grams of oxygen. Right, so again, the reason we did that is to get moles. All right, if you look on the periodic table, phosphorus, you don't really need to be too exact on these because we're looking for the formulas, chemical formulas, so we can just round if it's pretty close to a whole number. 31 grams per mole, and so that's going to cancel out. And let's just plug that in our calculator. 56.38 divided by 31 is going to be 1.8 moles for phosphorus. And then let's go over here. For oxygen is 16 grams per mole. So the grams cancel out. We're trying to get moles. 43.62 divided by 16 is going to give us 2.7 moles for oxygen. All right, so if we had the empirical formula right here, if we stop right here, it would be P, hold on, I'm skipping a step here. All right, so you want to take the smallest number, which is for phosphorus is 1.8, and see how many times that phosphorus will go into all the other ones. All right, so it's going to go into itself once, and it's going to go into oxygen twice. Oh, sorry, that's not. What am I doing? That's 1.5. Right? Yep, 1.5. Okay, so right now, if we left it like this, our empirical formula would be P10 1.5, and so that's not a valid formula. Can't have fractions in our formula, so we can multiply through by 2, all right, and then that'll give us an empirical formula of P2O3. So there's our answer for the empirical formula. All right, so now we need to figure out what the molecular formula is using the molar mass. All right, so we have to give you that information. So that's 220. All right, so the molar mass is 220, and that's of the whole molecule. All right, so what we're going to do is see how many times the empirical formula mass, which is the lowest ratio of the molecule, goes into it. Okay, so phosphorus is 31. And there's 2 of them in the empirical formula, so that's 62. And then there's 3 oxygen, that's going to be 48. All right, so the empirical formula mass is 48 plus 62, and that's going to be 110. Right, so you see it fits nicely in there, and so in other words, the molecular mass is twice as heavy, you can say, as the empirical. So the molecular formula must be P4O6, and there's your answer to the molecular formula. All right, the rest of these are should be much faster because they're just conversions. Right here, we're asked to convert molecules to moles. Okay, molecules, atoms, or any type of representative particle to moles is Avogadro's number. So let's start with the number given, 2.4 times 10 to the 24 molecules. And we'll try to get rid of molecules and end up with moles. So we need molecules to be on the other side of our conversion factor so we can cancel it out. And we want to be left with moles. That's the desired unit. All right, so 1 mole has 6.022 times 10 to the 23rd of whatever it is that you're counting. All right, so I'm going to plug this in step by step, assuming, I'm not going to assume anybody has a fancy calculator. So 2.4 divided by the coefficient there, 6.022. Oops, 0.399. Okay, because only 2 sig figs. All right, sorry. Let me go back. That's just going to be 0.40. Right? Times 10, that's our base. And when we divide bases with exponents with common bases, we subtract the exponents. All right, so 24 minus 23 is 1. Okay, 0.4 times 10 is 4.0 moles. All right, percent composition. Percent composition of nitrate from out of the whole compound is calcium nitrate. So calcium is Ca, has a 2 positive charge. Nitrate, that's on your reference sheet, that's NO3, and that has a 1 negative charge. All right, we're going to crisscross these numbers to get the ratio, and the formula for calcium nitrate is going to be CaNO3. There's 2 NO3s. All right, let's find the molar mass. All right, calcium 40.01, sorry, 40.08. It wants 3 sig figs, so I'm going to take this out to 4 digits. All right, nitrogen is 14.01. Let's just go there, 14.01, and there's 2 nitrogens. All right, so that's 28.02, and oxygen is 16.00. Right, and there's 6 of them. That's 96. All right, so here is our nitrate component. No, well, actually, we're going to have to add up this whole thing. So let's do that. 96 plus 28.02 plus 40.08. The molar mass of the entire compound is 164.1 grams per mole. Now the nitrate component is just going to be 28.02 plus 96. That's 124.02. All right, so to get the percent composition, it's going to be just the nitrogen component, 124, over the entire thing, 164, times 100 to convert that number into a percent. And it's 75.6%. All right, we're given liters, convert to moles, right? And if we have a gas at STP, the conversion factor is 1 mole of any gas at standard temperature and pressure is going to take up the same amount of space. That's Avogadro's hypothesis. All right, so let's start with the measurement given, 625 liters of hydrogen gas. And we want to get rid of liters, put that on the denominator of your conversion factor and the desired unit on the other side of that. Okay, so 22.4 is how they're, these conversion factors have to be equalities. They have to equal each other. Okay, so liters cancel out. 625 divided by 22.4 is how many sig figs? 3 sig figs. The answer is 27.9 moles. Another conversion. Let's go with blue. Grams to moles. We need the molar mass. You need your periodic table. All right, let's get the formula first. Aluminum has a 3 positive charge. Oxide, notice the ID, that's oxygen. That's a 2 negative charge. Crisscross those charges to get the ratios of the elements. So it's Al2O3. All right, let's get the molar mass. Do it right over here, off to the side. We're going to need 3 sig figs in our answer. I'll just go to 4 digits here. 26.98 times 2 for aluminum. 53.96. All right, don't have room for the units. 16.00 times 3, 48. All right, let's add this up, get our molar mass for aluminum oxide. 101.96 grams per mole for aluminum oxide. All right, now we can just plug and play. Plug these numbers in. 593 grams is what we're given. We want to turn that to moles. All right, well, grams got to go on the bottom, and moles got to go on the top. All right, and it is 101.96 grams in a 1 mole of aluminum oxide. So 593 divided by 101.96, 5.82 moles. That's really close to 5.81. So if you trimmed the number off a little bit, we'll give you 5.81. That's acceptable. Depending on what periodic, how many digits you went out. All right, but that's probably a better answer. Okay. All right, giving you moles, go to volume. Moles to volume, molar volume. Moles to volume. All right, just double check. It's a gas. It's at STP. All right, so we can use molar volume. All right, 2.50 moles of carbon monoxide. All right, doesn't matter what gas it is. Right? We want to get rid of moles. That goes on the other side. And we want volume, so liters goes on. Let me see. All right, so 22.4 liters is equal to 1 mole of any gas at STP. 2.5 times 22.4. 56, how many digits? We need one more sig fig, so 56.0 liters of carbon monoxide. Looks good. The housekeeping crew is like staring in my room like, when's this teacher leaving? All right, maybe I should let him clean the room. I'll be right back. He's gone. All right, so next problem. What are we doing here? Moles to mass. Moles to grams, moles to mass, mass to moles. Molar mass, periodic table. All right, formula unit for dinitrogen, that's N2. Monoxide is O1, and we don't write ones, so there you go. Let's get the molar mass. We need 3 sig figs, though. I'll go out to 4 digits. All right, nitrogen, we just did this, so 14.01 times 2, 48.02. Oxygen is 16.00, and there's only one of them, so let's add them up. 64.02 grams per mole is the molar mass for dinitrogen monoxide. All right, let's convert this moles to grams. All right, moles, get rid of that, putting it on the other side, and we want grams. All right, there's our conversion factor we're going to use. 64.02. Answer is 12.8 grams of N2O. So 12.8 grams is fine. You don't have to write the substance. Although when we get to stoichiometry, that's chapter 12. That'll matter, but not yet. All right, moving on. Gaseous compound, another one at STP. So molar volume is in play here. All right, but we're given what is this? We're given density and it's asking us for molar mass. So let's set it up. Grams per liter, that's density, and we want to take that to molar mass, which is grams per mole. All right, so notice we want to keep the grams. We don't want to get rid of that, but we do want to change liters and end up with moles. All right, so we need a conversion factor, just like the ones in your practice set. Yeah, get rid of this arrow. All right, just like the ones in your practice set. We want to keep the grams, but we want to get rid of liters. Get rid of liters, we need that in the numerator. The desired unit is moles. Okay, how convenient, right? 22.4 liters equals 1 mole. Cancel out the liters, and we're left with our answer in terms of the desired unit, grams per mole. All right, 3.58 times 22.4. 80.236, right? Okay, so grams per mole are the units we didn't cancel out. There's your answer. It's like, that looks like the same problem from our practice set. We're done with the open-ended. All right, but we still got to calculate. How many atoms? And we're given this one's not bad. All right, 4 molecules. Well, there's 1 molecule. 1 molecule has 8 hydrogens. If you had 4 of these, then that would be 8 times 4 is 32. Oh man, I thought I'd do another conversion. All right, answer is 32. Molar. The mass of 1 mole. All right, I hope nobody got that one wrong. At STP, all right, all of these gases, H2, O2, N2, F2, these are all diatomic, but it doesn't matter because if you have gases, and which these are, at standard temperature pressure, they're all going to have the same 1 mole. It's all going to have the same volume. All right, so let's see. Is that a choice? It's not a choice. But they are going to have different densities because density is based off of your molar mass. All right, so they're all going to have different masses because that's based off your periodic table. So that's true. All right, this one makes it, this second choice, they're all going to have the same volume, so that's not right. That's not the correct answer. These are not monatomic atoms, they're diatomic. No, 1 mole is just Avogadro's number. Okay. All right, large weather balloon filled with helium has a volume of liters. Has a volume. It's given us volume. Oh, it just wants another conversion factor. All right, we don't need to calculate anything. How do we get rid of volume? How do we get rid of liters? And find mass. All right, liters. All right, if we have liters, to get rid of it, all right, we need a conversion factor with liters on the bottom and the desired unit on the top. All right, it's saying we desire mass, so we need grams on the top. All right, do we have liters on the bottom? This one looks good. Grams on the top, right there. All right, let's just check through the other ones. We don't have liters on the bottom. We have liters on the bottom, no grams on the top. Grams are on the bottom. That's no good. Liters. All right, there's your answer. These are always a bit tricky because they're asking you for what is not something. All right, empirical formulas are the lowest ratios. All right, there's a 2, there's a 1, there's a 4. That's an empirical formula. You can't reduce that. All right, that is empirical. All right, a 5, a 6, a 5, and a 1. All right, 6, 5, and 1. Can you reduce that? No. Then it's the lowest whole number ratio. That's empirical. All right, 2 and 4, clearly you can reduce that. 2 and 4, you can reduce that to 1 and 2. So you can, the empirical formula would be that. That would be the empirical. In other words, this is the answer because it's not empirical. All right, last one. We have a 3. We have a 1 after the P. We can't reduce ones. So your answer is dinitrogen tetrahydride. Okay. Compound has an empirical formula and molar mass. All right, we need to find the okay. Remember, if we want to get empirical formula, molecular formula, we take the molar mass, which is always given, and see how many times the empirical formula mass goes into it, because that's the lowest ratio. All right, well, it's giving us the molar mass is 172 grams. All right, we got to figure out what this empirical formula mass is. Pick a different color. Let's go here. All right, carbon 12. And when you're doing formulas, you don't need a million decimals. So 12 times 2 is 24. H is 1 times 3 is 3. And oxygen is 16 times 1, 16. All right, so the empirical formula mass is 24 plus 3 is 27. 53, looks like. Oh, 43, I'm sorry, 43. All right, so there's your mass of your empirical, which is your lowest ratio, and this is the actual mass of the molecule. So how many times is 43 going to 172? It should be pretty close to a whole number, but if not exactly. All right, 172 divided by 43 is 4. Oh, it's exactly 4. All right, so we just gotta, there's your empirical, and just, it's 4 times that. So it's gonna be C8H12O4. Is that a choice? There it is. Equal volumes of gases at the same, that's a volume occupied by 1 depends on the molar mass. Oh, students, these are just copied from your worksheets. Please, if you're not doing them, do your review worksheets. That's never true. It only depends on the volume only depends on the number of particles, which is NSTP, but it doesn't depend on the mass. Okay. Same empirical formula. I don't know why, but like this one gets a bunch of students every year giving you the same question. It's, I don't know. Well, these can't be empirical formulas because they don't have they're not the same elements. Carbon and sulfur, they're different. All right, let's reduce this. 4 and 10 reduce to 2 and 5. Well, that's 5. That's opposite. That's not it. That's not it. 7 and 4 reduce to 1 and 2, and 1. Here's your answer. The empirical formula for both of those is CH2. This is your answer. All right, and this one is not the answer. Empirical formula is the lowest whole number ratio. All right, so periods 1 and 3, you all got credit for this one. I think there was a typo at the time, so we'll figure out how to. All right, but everybody else, this is what is true. 1 mole of any gas at STP. All right, well, it's going to take up 22.4 liters. That's true. All right, because it's nitrogen, right? Molar mass is going to be 28. That's 14.0 times 2. All right, so the 1 mole is going to have 28.0 grams. That's the molar mass, so that's true. All right, and that's the number of a mole, so that's also true. So they're all true. But you can only click on one, so there it is. Is that the last one?